Hello, everyone. I am Michael Ibrahim, and today I will be talking to you about our Federated Distribution Robust Support Vector Machine, or FDR-SVM for short. This is a joint work with Dr. Geraldo Rosas, Dr. Neki Gabriel, and Dr. Wei Jun Xie. We will start by introducing our motivating problem for this work, where we consider an original equipment manufacturer, or OEM, which manufactures industrial equipment for potential use in manufacturing, energy, or healthcare, among other domains. We also consider multiple clients that are interested in purchasing and utilizing identical pieces of this equipment. The OEM manufactures identical pieces of equipment and sends them to the clients, where they are operated and operational data is collected from them via onboard sensor suites. Now, the OEM is interested in utilizing this operational data from the clients to train a classifier, allowing it to offer fault diagnosis services to the clients as part of a lucrative long term service contract. However, in doing so, it is faced by two distinct challenges. Firstly, the data is distributed and cannot be shared due to privacy concerns and bandwidth limitations. Secondly, the data can be affected by high levels of uncertainty due to sensor noise affecting the features and potential labeling errors affecting the labels. Therefore, in this work, we attempt to combine the fields of federated learning and distribution robust optimization to allow us to train the model in a distributed fashion while modeling perturbations in the empirical distribution of the data to anticipate and hedge against uncertainty. More specifically, we seek to develop a distribution robust classifier that can be trained collaboratively in a federated fashion by multiple clients and a central server. Our key contributions in this work are that we firstly introduce a novel ambiguity set that naturally leads to the separability of the min-max problem associated with distribution robust optimization. We then introduce two training algorithms to train our proposed model. One is based on the subgradient method, and the other is based on ADMM. In proposing those algorithms, we derive tractable computations to be performed by the clients and the server, and we analyze their convergence behavior and worst case time complexity. Finally, we demonstrate through extensive numerical experimentation that our model enjoys superior performance to various existing federated benchmarks, highlighting its practical significance. Mathematically, our model takes the following form, where psi is a random variable governed by a true and unknown distribution p, and is a tuple of the feature vector and the label. We consider the hinge loss function associated with the SVM, and we denote the ambiguity set by A sub g. This ambiguity set is a key ingredient in our problem, as it is typically defined as a single ball of distributions centered at the empirical distribution of the training data. But this form is unnatural for the kind of distributed problem that we consider here in this work. Therefore, we propose a novel ambiguity set that leads to problem separability. In defining our ambiguity set, we begin by modeling the global true distribution governing the data as a mixture of the different true distributions at each client. We then allow each client to model local uncertainty via a local Wasserstein ball centered at their local empirical distribution. Finally, we model the global ambiguity set as the set of all mixture distributions whose components belong to the local ambiguity sets. In the paper, we show that this ambiguity set enjoys a nice out-of-sample performance guarantee and that it directly leads to the separability of the problem we introduced earlier. As mentioned previously, the two distinct algorithms we propose to train our model are a subgradient method or SM algorithm and an ADMM algorithm, for which we also propose a modified version to theoretically guarantee convergence at the expense of additional and potentially redundant regularization. At its core, the simplified idea of the SM algorithm is that clients compute local subgradients, which they then send to the central server. The server then aggregates those subgradients and updates the global model via a subgradient step, and it then broadcasts this updated global model to the clients, and the process repeats until convergence. Indeed, in the paper, we show that this algorithm converges to an optimal solution of our problem, given that the step size diminishes at an appropriate rate. We also show that this convergence happens in polynomial time. Now we move on to the ADMM algorithm, where the core simplified idea is that each client trains a local model, and the clients share those local model parameters with the central server. The server then aggregates those model parameters and broadcasts an updated global model back to the clients, and this process repeats until potential convergence. Indeed, we show in the paper that only a modified version of this algorithm is theoretically guaranteed convergence, although the unmodified version of the algorithm also converges in practice, as we show in the numerical experiments. We also show that this convergence of the modified version is achieved in polynomial time and is in fact faster than the SM algorithm. One of the experiments that we perform uses multiple UCI datasets to benchmark the performance of our algorithms against a single centralized model and multiple federated algorithms from the literature. We observed that at least one of our proposed algorithms outperforms all the federated benchmarks for most datasets, highlighting the practical impact of our model. Our key takeaways in this work are that we propose a novel distribution robust classifier that can be trained in a federated fashion thanks to our novel ambiguity set. We develop two distinct training algorithms to train our model, and we demonstrate through various numerical experiments that it outperforms existing methods for most settings evaluated. Thank you very much for tuning into this video. Further information about the paper and the code can be found in the description.